Okay, welcome AP Chem kids. We're going to talk a bit about percent dissociation, or in an acid sense, it's actually an ionization. You're forming hydrogen ions. Uh, the percent dissociation is defined as the amount that's dissociated over the initial concentration times 100, which is also the same equation we did for a validation of within 5% of Ka tables. But what's unique about this percent dissociation is that for a given weak acid, if the percent dissociation increases as the acid becomes more dilute, and I want to kind of prove that to you guys as we go through a couple of example problems here. We're going to talk about, actually it's just one example problem, and we're talking about acetic acid. Acetic acid, you have a 1 molar concentration of acetic acid with its Ka value as being 1.8 times 10 to the negative 5, and it's asking you to calculate the percent dissociation. So if we're taking a look at that and we're saying, okay, the major species would be water and acetic acid, and based on what I know about the Ka value of acetic acid being 1.8 times 10 to the negative 5, and what I know the Kw of 1.0 times 10 to the negative 14, the acetic acid is a stronger acid than the water. So that means the acetic acid is going to dominate the hydrogen ion concentration, and it's going to be the dominant producer of the hydrogen ion concentration for this reaction. Okay, so we're going to use the Ka for the acetic acid, and I skipped a step here because I didn't write out the equation for the acetic acid, but it will show up here in a minute in our rice tables. And the Ka, this would be the Ka expression, is 1.8 times 10 to the negative 5, and that would equal, as we know, any Ka or Keq is products over reactants. So the hydrogen ion concentration times the acetate ion concentration over the acetic ion concentration. Okay, so we are aware of that. Now I'm going to write a rice table, and here's my equation. Okay, so this is the dominant equation. It's the one that's going to produce the most hydrogen ion. It's the acetic acid. And as I take a look at, let's undo that again. Not being careful with my, let's undo this one. I'll undo. Okay, now we're going to, fill out my rice table. Okay, so when we know the initial concentration is 1, we know that we haven't allowed for the hydrogen or the acetate ion to dissociate yet, but we know that there is going to be a change, so that's where I have the minus x and the plus x. And the equilibrium line would be that 1.0 minus x would equal x times x. So now, what would go into the Ka expression is that equilibrium line. So when I put that equilibrium line in, I would say 1.8 times 10 to the negative 5, that's the Ka for acetic acid, is equal to x times x over 1.0 minus x, which in fact, using the easy way, knowing that 5% rule, we can say that that's x squared over 1, which makes the solution much easier than having to do the quadratic equation. And I would end up with x equaling 4.2 times 10 to the negative 3. That would have, and here's a big rule that I just violated here, is that should have a unit of molarity, okay, because it is a concentration. That is the hydrogen ion concentration for 1.0 molar acetic acid. So now the percent dissociation would be defined as that 4.2 times 10 to the negative 3 over the initial concentration of the acid, which was 1 times 100, and you'll notice that you get 0.42%. All right, pretty simple. Again, just it's like calculating a weak acid, and then we figured out the percent dissociation. But now, what if we're still talking about acetic acid? The Ka is still 1.8 times 10 to the negative 5, but look at the concentration. Concentration is 0.1 molar. acetic acid. Okay, how is that going to change? Well, it's still all the same thing. I mean, the Ka hasn't changed. Your two major species are acetic acid and water. The Kas haven't changed. So what's dominating this reaction or producing the most hydrogen ions is the acetic acid, because that Ka is so much higher than water. So what happens here is that when I do this rice table, now notice my concentration is 0.10, a 0 for the initial concentrations for the reactants or products. And then I look at the change, again, the minus X and the plus X. And then at equilibrium, the 0.1 minus X and X times X. So that rice table changed just slightly because the concentrations changed. And now when I plug that into my Ka expression, I get 1.8 times 10 to the negative 5 is equal to, roughly, basically, x squared over 0.1, using that 5% rule, assuming that that value of that x is so small compared to still that 0.1. Even though 0.1 is less than 1, I get that, it still doesn't dissociate as much. It's still going to be within that 5% rule. So when I calculate this, and again, I'll just make sure that I put an M there because it is a concentration, the hydrogen ion concentration ends up being 1.3 times 10 to the negative 3 for the concentration. Let's just go back to this page. What was the hydrogen ion? Here it was 4.2 times 10 to the negative 3. So interesting, again, that hydrogen ion concentration is larger for the 1 molar, but that's because it was a higher concentration. And look at what the percent dissociation was, 0.42. What's going to happen when I take that 1.3 times 10 to the negative 3 and I'm going to divide it by the initial concentration, which was 0.1, now the percent dissociation ends up becoming 1.3. And so the more dilute that the weak acid is, there is going to be more dissociation that happens, okay? So 2 important points to remember. The concentration of the hydrogen ion is smaller for the 0.1 molar than it was for the 1.0 molar, what we expected, but the percent dissociation increases with that 0.1 molar concentration. And your book will talk about, there is a Le Chatelier piece to this, that when water is added to the reaction, you basically are diluting the acid, so it's going to want to dissociate more. If you kind of think about it that way in terms of Le Chatelier and concentration. So just kind of in summary, the effect of dilution on a percent dissociation of a weak acid solution. So this is a nice little graphic that as you are diluting your weak acid, the percent dissociation will definitely increase, as just proven by those 2 example problems. I hope this helps, and I hope you're having a good day. Thanks.